Yeah, that sounds great. So I don't know if you took a look at the slides I loaded, but they're super simple, very similar to what Joe was doing last time. I'm basically asking people to get crap. If they do or don't, then we can choose to. I don't know.
Did you want to ask for adoption right now?
I mean, if people don't object, I think I would ask if they like. I forget exactly what I put on the slides. Is this useful? Yes. Should this happen? I guess that's sort of implicitly do you want to?
And I guess we don't have to do it. We can just take that feedback.
Yeah.
Choose
Yeah.
Hello. Welcome to the PEARG session. Thank you for coming, everyone. Getting right into it. This is the note well. I'm sure you've already seen this from the morning session, but if you haven't, please familiarize yourself with this. Keep it in mind going forward for the session. A couple of administrative notes before we get started. Blue sheets are somewhere up here. Did you pass them around? We will pass the blue sheets around. Please fill them out. We need a JavaScribe. We do? Okay, great. As well as a minute taker. Oh, great. Excellent. This is the agenda. Pretty straightforward. We're going to have a couple of presentations from sort of researchers in the area, and then some individual draft presentations. Does anyone have any comments or adjustments they'd like to make before we get started?
So I think, so Joe offered to do a quick update for one of the adopted drafts that we have. Maybe want to come up? So draft censorship is an adopted RG draft, and Joe offered to give a quick overview and update.
Yeah, so this is a draft that's been alive for a very long time. I've made absolutely no progress since the last IETF because I changed jobs, and my job now is been difficult, so to speak. But anyway, I have a list of issues. I think I just threw in the chat. I may not have hit return. Christian, if you want to hit return on my computer, they'll post. But I'm hoping to get through those in December, and that's, I guess, the update. Thanks.
Alrighty, thanks, Joe. When the update comes, maybe folks can take a look, provide some feedback on the list, and that would be helpful going forward. With that, we can get into the presentations. So if the presenter for the first talk could please come up.
Is Professor Shokri here? It's not.
That's unfortunate.
Yeah.
I guess
Do we have Professor Liu? Do you want to go first? Perfect. You know how this works?
you can just move.
Yeah, you can just let us know when you want to move. I don't think this is working.
I have a
You can try. Yeah, you can just stand in the.
okay. Hello everyone, and I'm Lu Xianhui from Scripps NTU. Thank you for invitation. And today I will share our research on privacy preserving via homomorphic encryption. And my talk was divided into two parts. First, I will introduce some very background of homomorphic encryption, and then I will introduce the main applications of homomorphic encryption. And now let's begin with the first part. Okay, just a simple definition. What is homomorphic encryption? And both of these two words are very ancient. For example, encryption is the process of encoding of a message, a meaningful message into a randomness-like message. For example, we can use the Caesar cipher, which was invented about 2,000 years ago. And in this encoding, the message "Welcome to NTU" can be transformed to a meaningless message. The key is just to shift every character 3 positions. And what is homomorphism? Homomorphism is a structure-preserving map. And it will preserve the algebraic structures and combined together, we'll get the homomorphic encryption. So that's the definition of homomorphic encryption. And if we can preserve the algebraic structure, then we get the homomorphic encryption. That means if we have the encryption of the message 1 to message n and also a function f, we can just simply compute it on the encrypted data and get the encryption of FM, like this. So now we have the definition of homomorphic encryption. It is a special kind of encryption algorithm that supports ciphertext computation. There are mainly two types of homomorphic encryptions, and the first type is partial homomorphic encryption, and the second type is fully homomorphic encryption. For the first type, it only supports single operations such as addition or multiplication, and it was used in data aggregation or some construction of MPC protocols. And it is very easy to design such a kind of algorithm. And but for the second type of homomorphic encryption, the fully homomorphic encryption, we require to support unlimited numbers of operations, and it can both support multiplication and addition. And a little surprise, it is very difficult to design such kinds of encryption algorithms. It was named as the holy grail of the cryptography area, and remains as an open problem for about 30 years and just resolved by Gentry in 2009. And between these two types of homomorphic encryption, there are many middle types of algorithms. For example, the famous somewhat homomorphic encryption, it can support limited numbers of operations, and it is also widely used in the area of privacy protecting. Okay, this is a brief history of homomorphic encryption. It is nearly as old as the public encryption itself. It was first proposed in 1978. And after 30 years development, the first fully homomorphic encryption occurred. And after that, about 10 years, we have the fully homomorphic encryption developed very quickly. And now we have many public implementations, which we can get from the GitHub or any elsewhere. And the standardization process is already on the way. And for the standardization, for the partial homomorphic encryption, we already have a standard that was published by ISO this year. It includes two algorithms, which is the exponential algorithm encryption and the Pali encryption algorithm. And for the case of fully homomorphic encryption, and the researchers and the government have already organized 4 workshops on the processing. And okay, this is a list of the mainly current open source libraries for homomorphic encryption, and for integer or finite field operations, we have SEAL and HELAB and the HAN algorithm. And for the Boolean gate operation, we have TFHE and FHEW. And these are all public in the internet, we can get freely. And now to use the homomorphic encryption in real applications, the most factor we care about is performance. And there are mainly 3 kinds of operations: the integer arithmetic and the approximate arithmetic and the Boolean gates. And for arithmetic operations, currently we have very fast computations on integers or fixed point numbers for limited times of operations. If we want to achieve unlimited time operations, then it was not that efficient because of the slow bootstrapping technique currently. And for Boolean circuits, the bootstrapping seems very fast. For example, we need 13 milliseconds for one operation of the any kind of gates. But since any real application, if we construct it by using the Boolean gate, then it may take many gates operations. So the real applications may be less efficient. Now let's see some test results of the different kinds of libraries. If we want to do the integer addition or multiplication, for example, we want to do the integer addition, then we can use the exponential algorithm or Pali, or just a simple lattice-based encryption. And the performance is very good. For example, we only need 1 microsecond for the exponential algorithm, and we may need 8 microseconds for the Pali, and less than 1 microsecond for the lattice-based encryption. But these 3 kinds of libraries cannot support the operation of multiplication. And if we want to support multiplication, then it will be less efficient. For example, the SEAL library can complete the integer addition in 6 microseconds, and also for 1 millisecond for the operation of multiplication. And if we want to do unlimited operations of addition and multiplication, then we can use the HELAB. It may take 5 milliseconds for the addition, and about 200 milliseconds for multiplication. It is much slower. And if we want to do the integer addition by using the basic Boolean gate, then it takes about 1 second to complete the addition operation, and about 20 seconds for multiplication. So it's much slower. With the Booleans, also the Boolean circuit is much slower, but we can construct any kinds of operation by using the Boolean gates. For example, we can design the circuit for integer addition and the float number addition and the subtraction and the multiplication, or even the square root operation or the sine function or the exponential function. That we can construct any kinds of functions by using the Boolean gates. And it is much slower. For example, the exponential function may take about 174 seconds. Okay, now let's begin the second part, how to use homomorphic encryption to provide the privacy protecting. Generally speaking, we can solve the privacy problem by using fully homomorphic encryption very simply. The framework is firstly, in the first step, we just encrypt our data, and then we do any kinds of operations on the ciphertext. And finally, the user just to decrypt the ciphertext and get the results of the computation. So it is very simple, but this kind of realization is always not very efficient for our real applications. And so we need to design different kinds of protocols, specific protocols for different kinds of applications. For example, in the data collection, data retrieval, data sharing, and the data mining, we may need to design the protocol of data aggregation, private information retrieval, and the private set intersection, and the privacy preserving computation protocols. To design this kinds of protocols, we may use many kinds of primitives. For example, the differential privacy technique, the searchable encryption, functional encryption, and even the oblivious RAM and the searching secret sharing and oblivious transfer or garbled circuit. Today, we are mainly focused on the homomorphic encryption. Now let's begin with the very simple application that occurs in the data collection. And the left is the famous feature published by NIST. It shows that the power usage gets from the smart meters may leak the information of the users, what you are doing in your home, for example. From this feature, we may get the information that the user maybe gets up in the morning before 8 and prepare his breakfast and then washing and then about when to eat his lunch and when to get to sleep. So in this scenario, we need to aggregate the data, the power usage of each user and get a summarization, send this summarization to the control center. And this is mainly the most simple and the most mature application of homomorphic encryption. In this case, we only need additive homomorphic encryption. For example, we can just add the usage of each home together, and according to the tables previous, we can see that addition is very efficient. And in the case of data retrieval, for example, the user wants to get some public database, access some public database. Although the data itself is public, but the access pattern will leak the privacy of the users. For example, if we are access a patent database, then the server may know what kind of product this company will be planned to construct. And theoretically, it seems that the only way is to download all the data in the database. Because even if one item is not touched, then the server may know that the user is not interested on this kinds of data. So this is very efficient. Previously, we can solve this problem by using multi-servers. And we need to assume that these servers will not conclude together to recover the privacy of the users. But this kind of assumption is not reasonable for most of the real applications. So let's see how to protect the privacy by using homomorphic encryption. The user only needs to encrypt every index by a ciphertext. And for the item he wants to get, he just encrypts one, for example, the ICE index. And for all other index, he just encrypts 0. And then the server will multiply each data to the ciphertext. And we know that for the index I, the xi will be encrypt. This position will get encrypt of xi. For all other positions will be the encrypt of 0. Then the server summarize all the ciphertext together and only to send one ciphertext to the user, and then the user can decrypt and get what he wants. So in this simple protocol, and the server, the communication bandwidth that the server send back to the user is only one ciphertext, but the user still needs to send many ciphertext to the server. We can optimize this protocol very simply. For example, we can divide the data in the server into 100 blocks. And in this case, the user only needs to send 100 ciphertext, and the server only need to send 100 ciphertext back. So instead of sending about 10,000 ciphertext, in this case, we only need to send 200 ciphertext. It's a balance between the two passes. And we can make, if we use the more powerful fully homomorphic encryption, we can make this protocol still simpler. In this case, the user only needs to encrypt the index he wants, only one ciphertext, and the server, for each index, he just finish the compare operation. And if I equal to j, then it will be an encrypt of 1. And for all other positions, it will be a ciphertext of 0. So, and he still summarize all the ciphertext and send the result back. So in this protocol, we only need two ciphertext, and the communication bandwidth is very efficient. But we have already seen that fully homomorphic encryption may be not that efficient. So we can improve this protocol by a very careful design of message encoding. That is, we can encode the message instead of encrypt the message directly. We just encrypt it to a polynomial. For time limit, I will not have enough time to describe the technical details, so I only describe this equation. And in this case, we only need the additive homomorphic encryption and to complete the equality test and achieve the bandwidth efficiency and the computation efficiency together. A more complex scenario may be the user wants to outsource his data to the server. In this case, all the data X is also the encrypt a ciphertext, and in the last scenario, it is a plain text. So in this case, we may need to do much more about the design of the protocol and the encoding to avoid the usage of multiplication and only use the computation for additional homomorphic encryption and makes the protocol more efficient. And in this case, besides the operation of a read operation, the user maybe want to update his data stored on the server. Then the write operation may also leak his privacy. So to protect this kind of privacy, we may need the more complex oblivious RAM techniques, and we will not describe this technique here. Okay, that's the case for data retrieval. Now let's see the case for data sharing. In this case, Alice and Bob both have two private data sets, and they want to compute the intersection. It is a very simple scenario. Obviously, we can solve this problem by using the hash function. For example, Alice just said that each of his value, the hash value of each of his data to Bob, and Bob sent back each value, the hash value to Alice, and then each of them, all of them can just compare the hash values and to find out their intersects. But this protocol is not secure. For example, if the space of Alice and Bob's in the set is not big enough, then we can search all the possible inputs and find the data. And we can resolve this problem by using a very difficult Hellman key exchange like protocol. And this is secure, but Alice and Bob also need to do many kinds of modular exponential computations, which is very time consuming. And with homomorphic encryption, we can in time?
Only a few more minutes.
Okay. We just finished. So we can design a protocol based on homomorphic encryption and do the equality test. And Alice does send the encryption of his data, and Bob does the minus every of his data and multiply a random number. If X is equal to Y, then Alice will get the encryption of 0. And if X is not equal to Y, and Alice will get a random number. So he'll find out their intersections. Okay, with the quality test that we designed in the data retrieval protocol, we can design a more efficient protocol to resolve this kind of applications. And finally is the privacy preserving in data mining. This is the two phases in neural networks, and the training phase and the prediction phase. And we mainly focused on the prediction phase because the training phase itself in the plain text is still very time consuming. And but the prediction is in plain text is efficient now. And the first step, we need to analyze what kinds of computations we'll need in the application of neural networks. For example, the convolution layers is simply the computation of matrix multiply a vector, and the ReLU layer, is we need to comparison and the selection. And in the full connection layer, we also need the computation of matrix multiply vector. And so we can design a very simple protocol to complete the computations based on the Boolean gates. Although we can see that it is very inefficient. And we can achieve the operation of the linear operation by using additive homomorphic encryption. But in this case, we cannot compute the active layer or the sigmod or the ReLU function by using the additive homomorphic encryption. This is what we are still research now. And finally, give a conclusion. With homomorphic encryption, firstly, we can achieve the Boolean circuit gates, the XOR and the AND, and the arithmetic, the addition and multiplication. And with these algorithms, we can achieve any kinds of algorithm or Boolean circuit. And then we can solve any kinds of generic problem with a generic solution. And we also can design specific protocols for each kind of applications, and we can get efficient solutions. Okay, thank you.
All right, yeah. Unless anyone has a very, very quick question or comment, perhaps we can move on to the next presentation. Thank you very much for coming and talking.
Okay, thank you.
Can the presenter for the first presentation come up? Yes, thank you.
All right. Hello, everyone. My name is
Dr. Shokri,
Reza. And,
you'll need to stay in the pink cross.
Oh, here. All right. Okay.
It's for the benefit of the remote people.
My name is Reza. I'm an assistant professor at NUS. I run the Data Privacy and Trustworthy Machine Learning Lab And today I'm going to talk about the privacy risks of machine learning, but I need to start with, oh, how does this?
No, try it now.
Okay, perfect. So I need to start with a very important concept of inference attacks. If you have some data about individuals, it's possible to combine it with some other information and use advanced statistical methods or machine learning algorithms to infer further information about those individuals. This has been shown many times in the research community and on different types of data. For example, on Facebook likes, you can infer information about personal data. And also, it could help to identify whose data is in the data set. For example, for location data, you just give me 5 random locations from your trajectories. You are almost unique in the world. All right. So this is basically the main risk of sharing the data itself. Either I can infer some sensitive information further than what is already in the data, or identify the individuals in the data set. So there has been a lot of efforts on how to protect data privacy. Data sanitization through removing sensitive information or removing identities has been one idea. But and there's a huge business on this by anonymizing data. But what is missing there is, what is the definition of privacy? Because the bad news is that by removing identities or sensitive information from the data, you don't make the data privacy preserving. Okay? Anonymous data or anonymized data isn't. Either is not anonymized, which means that the attacker can link the anonymized data to the true identities of the entities in the data set, or is not data anymore, which means that you have to destroy it so much to break the link between identities and the data. Basically, what happens is that an attacker has some background information that links it with the data that you release to infer information about the data, which is not in the release information. All right? And this can go for like different types of data. And recently, we have also shown that machine learning algorithms can extract patterns from the data, even if it has been obfuscated a lot. So if you see these kind of faces in the that are used for anonymizing data, it's not anonymous anymore. So machine learning models can reconstruct the identity of the individuals. So in general, this is what I call inference avalanche. There is some piece of information that is released. There is some information that the attacker has. Combined together can lead to more inference about the individuals whose data was used for computation. It doesn't matter what type of computation. I'm going to give you some information about, statistics and machine learning. And for example, for statistics, you have some data, you want to release many statistics about the data records in your data set. The attacker can run an inference attack or to identify which data sets could have produced these statistics. And as you increase the number of statistics that about your data set, the plausible data set that could have produced these statistics reduces. And some of them have higher probability of being the true original data set. And it has been shown that the attacker can actually reconstruct the full data set with negligible error as the number of statistics increases, even if the statistics are noisy a little bit, all right? Or it can be used to identify whose data was used in the data set. For example, NIH used to release the statistical information about the DNA of individuals who are in their data sets. So the allele frequencies, if you're familiar with the DNA data. And from that, researchers managed to find out whose data is in that data set that resulted in this summary statistics, which are very harmless, right? So I'm just releasing the average value of each attribute. But if there are so many of those statistics, the attacker can actually identify whose data is in the data set. And this had consequences. A lot of data holders now stop releasing their data, stop releasing the statistics about their data, and so on and so forth. Now I just want to move to what is the topic of this talk that I want to briefly talk about, and that is the information leakage through machine learning models, right? So you would say, well, if I'm anonymizing data, yeah, there are a lot of attributes which are in the data set. I understand how the attacker can join this data set with some other data set to reconstruct the identities. If you release statistics, maybe I can tell why this can lead to the inference attacks. But machine learning models, even those who design machine learning models, don't know why the machine learning models work, right? So then how can an attacker exploit the information which is embedded in a machine learning model to infer the data set that was used for training of it? So in the setting that we have is that we have some data set that we use using some training algorithms to construct a model that does, for example, a classification for us at the time of inference or the test. What you do is that you send some data points and the model tells you what is the probability of each class associated to the data that you have shared, right? Very simple, very useful. There are a lot of services out there, machine learning as a services provided by cloud service providers today that you don't even need to understand how machine learning works. You just upload your data, they train a model for you, and then you have this very simple API through which you can access this, all right? And also, you know, we know that machine learning is eating the world, so everyone is now using machine learning for everything, any data that they have. So it's very important to ask whether the predictions that I get from the model actually leak any information about the data that was used to train the model. But note that at the time that you get the predictions, the data is gone, right? So at first phase 1, we train the model. Now in phase 2, we just interact with the model. You send a query, get a prediction, right? So how can this leak information about the training data? I mean, before that, I need to clarify what leakage means, because when you interact with a model, you learn information from the model, right? You didn't know that this patient is susceptible to cancer. Now you know. You didn't know whether you need to invest in this plan or invest in the other plan, but now you know which one is more important, right? You didn't know these things before interacting with the model. So not any information that you learn from the model is privacy violating. So what is leakage here? If I can learn something about you by interacting with the model that I could have not learned if you were not in the data set, means that the model is leaking information about you, right? Because if I get some model and then I interact with the model and I learn that, you know, half of the population are male, half of the population are female, it doesn't matter if your data was there or not, right? So this is just generic patterns about the data. But if I learn that the chance that an individual, particular individual, has cancer, but I couldn't tell that by just looking at the general patterns of the population, means that the model is leaking information about that individual, all right? So this is what we call leakage. And one very particular way of measuring leakage is to tell whether, by interacting with the model, I can tell whether your data was used in the training set of the model or not, okay? And this is what we investigated. As I said, there is machine learning as a service. Google, Amazon, Microsoft, others provide this data. This service. And you have no idea what models they train, and the attacker has no idea to tell what models they train, but he can access the model through this API. So what we went and we designed an attack that can tell with a very high accuracy. So for this data, that was some customers purchased data that was used to train a model on Google and Amazon platforms with close to 90% accuracy. You could tell whether your record was part of the training set or not. And the only window of access to the model is just the predictions. I send a query, get a prediction. And from that, I want to tell whether some particular data was part of the training set or not. So this award-winning set of algorithms tell us that there's a huge risk of using sensitive data while we're training machine learning models. So it's not that because we don't know how the model is trained, therefore there's no way to extract information about the model. Some very simple statistics that I want to show to you is that basically the models are more confident on the data that they have seen compared to the data that they haven't seen. And this piece of information could be exploited by the attacker, right? So the behavior of the models with respect to the data that they have seen during the training is quite different from the behavior of the models with respect to the data that they see for the first time, right? And this statistical difference could be exploited by the attacker, and this is exactly what we exploited. If the model is released for various reasons, now you hear about transparency in machine learning, so they ask, okay, what model do you use for certain decision making? You might have even access to the model parameters. This is what we call the white box access to the model. You know how the model comes up with a decision, and you know, if you look at these different types of machine learning tasks, they extract all sorts of simple to very complex features about the data that help you then later on classify the data. And what we ask is whether the parameters of the model leak information. For those of you who might be a little bit interested in the techniques, basically there is a training algorithm, there's an optimization problem that we solve for coming up with a model, and that optimization problem, the way that we go through different values of the parameters until we solve the optimization problem and we find out the final model, totally depends on the data that was used for training the model. So the footprint of the data can be seen and extracted from the model parameters, and this is exactly what we looked at. And again, some other statistics that can show that the behavior of the model parameters with respect to train and test data is different. And what we did was that we looked at very well generalized models out there, the best machine learning algorithms that are out there for some benchmark data sets. And what shows is that the ones that are even the best in terms of accuracy, that generalize the best, leak the most. They have a huge capacity. Basically, these machine learning models have so many parameters to embed the function that they want to learn, and they use some of this capacity to learn the task. The rest is used to memorize information. And that's a footprint, right? So we went through all these different values of parameters by looking at the data, and later on the attacker can exploit this and infer whose data was in the training set and even reconstruct the data that was used during the training. So then I'm asking this question. If you look at different privacy regulations, it says that the personal data or any information which are directly or indirectly related to an identified or identifiable natural person. So basically the information that can help you to single out an individual and say, okay, this information is related to this particular individual. And now I'm saying, okay, the models enable us to single out individuals from any data set and tell, okay, this data was used in the training set. Now, can we just simply release models or use models in the cases where some attacker can have access to it or untrusted entity have access to it? It's a big question. Is model personal data? Should we treat models similar to the way that we treat raw data? Because what the attacks show is that you can infer a whole lot of information about the models from the models about the training data, right? So it's a big question here. So I want to just say a few words about what to do, right? So as privacy experts, the first thing that we do is to just identify why you need to use the data, in what process, and what is your trust model. Do you trust the machine on which you do the computation? do trust the entity that is going to see the end result of the computation. What is a trust model? And based on the trust model and based on why you want to use the data, we can design privacy-preserving computations that protect against these kind of inference attacks. Whether you're outsourcing the data, whether it's a collaborative type of computation, whether you want to do data analytics, or you want to enable data release for exploration and visualization. All of these need different types of tailored defense mechanisms. So for privacy-preserving computation, in order to protect against the attacks that I mentioned, what do? We need to make a choice. And one choice that we make is to just say, well, I'm fine if general patterns about the data set are shared, but I want to protect the information about individuals, right? We need to allow some information to be shared, otherwise the data is useless, right? The computation is useless. So what computations, what kind of information do I allow to be communicated? The general patterns, the ones that are not dependent on individual records. And at the same time, I want to protect information leakage about individuals. I don't want one data point to significantly change the result of the computation so that the attacker can exploit it. In other words, if you want to go and collect data or convince the customers or the data holders to provide data for you for your computation, you want to tell them that, well, whether you participate or you don't participate, right, the information that someone can learn about you by observing the result of the computation is the same, or more or less the same, right? Because you help us to learn the general patterns, but your specific patterns are not leaked. A few other techniques that I refer to them as sharing without sharing. You have huge data set, you want to release this data set, or you want to learn something from the data set. Instead of sharing the data, why not constructing another data set which is very similar but not the same as the original data? This is through the process of data synthesis. And the data synthesis itself should be done in a privacy-preserving manner so that the result, the data set that is released, cannot be linked back to the original data set, right? And we are designing techniques that can provably, using mathematical rigor, show that there is no way to link back the release data from the original data. And nevertheless, you can infer, you can construct models on the synthetic data, you can run statistics on the synthetic data, and then use it for whatever purpose that you have. Another one is collaborative learning. And the idea is that, and this is very important because in many cases, we have many entities that have data, but they don't trust each other to share the data with each other, right? But they have the same task. Multiple banks, multiple hospitals, multiple financial, even different departments in one organization. And the platform that we are designing allows these different entities to learn the same machine learning model together without sharing the data with each other, but sharing some hints about how they are constructing their models, but in a privacy-preserving manner, so that those hints also don't leak information about the individual records in their datasets. These are just two examples of how we can construct a mechanism that can enable privacy-preserving computation. I'll stop here and be happy to take questions. But if you want, you can also look at our website to find out more about our research results. Thanks. Yeah.
All right. Thank you, Reza. Are there any questions? Going once, going twice. Question from DKG.
Hi, Daniel Kahn-Gilmore, ACLU. Thanks for presenting this year. I think it's useful information and background for folks to have at the IETF. especially as we move towards things like software-defined networking and other kinds of mechanisms that might incorporate machine learning in ways that I'm personally kind of terrified of. I was curious about your point about personal data, whether you know if there's any attempt to classify. So one of the things that GDPR and other similar privacy regulations require or want to encourage is the ability to have your data removed from a data set. And I'm wondering if you think of models, machine learned models, as potentially containing personal data, if anyone has attempted to categorize different machine learning models as models that you could remove your data from. That is, not only can your information be added to the model to make the model more accurate, but that at some later date, you could take an existing model and knowledge about a person's information and effectively remove them from the data set. Is there any attempt to break that kind of, does the question make sense?
Yeah. So basically, there are two ways to look at this problem, right? One is that by construction, right, when I include your data in the training set, can I minimize the influence of your data to the model so that somehow approximately everybody's data is removed already, right? So I learned the general patterns, but the information about it in each individual or the influence of each individual on the model is bounded, right? So somehow everybody's data is removed, except that like there is this small epsilon information about each individual which influences the model. So that is one way to look at it. And the second way is, well, if I want to totally remove all the bits of information that you contributed to the model, can we provide a provable guarantee that now your data is removed? For certain types of models is much easier. For complex models, I don't know, such as deep learning, there does not exist a provable technique yet, but people are working on it. So this is a problem that researchers are working on it, on how to actually prove that all the information about your data is removed from the model. Because otherwise you can just retrain the whole model, but you don't want to do that, right? So how can I, with minimal effort, remove all the information and prove the guarantee,
You can only retrain it if you've actually kept all of your training data around, right? In which case that requires you to store even more personal data in order to retrain with a smaller subset.
So you don't want to retrain, right?
Yeah.
So what I'm saying is that overall you want to have minimal effort, but provable guarantee that the data is completely removed. Right. If you train it with differential privacy, as this is what we are doing now, then the influence is already minimum. Okay, so how much more guarantee can you provide? Then that's an open question, right, for complex models.
Trying to put together this talk and the last talk, I know there's been a fair amount of work on trying to build. Jesus. Hang on, just cannot. I'm gonna have to. I know there's been a fair amount of work on trying to build learning models that don't involve the central server ever having access to your specific data, using things like homomorphic encryption and other more techniques. Does that have any substantial impact on this problem? I.e., if you use those techniques, do you not have to worry about release of the models, or does that not solve the problem?
Yeah, so these are two different trust models, right? So who the adversary is, right? Is the adversary the one who is doing the computation, or is the adversary the one who is observing the result of the computation, right? So what I was talking about mostly is about the adversary who observes the result of the computation, right? So let's say, for example, if you have a central server that blindly trains the model for you, later on you use the model for certain applications, then the inference attack is against the one who can observe the model.
Sure.
Yeah.
No, I understand. But I guess my question I'm getting at is there are many situations in which the adversary is the people doing the site which is doing the training itself, right? Which is the machine learning site. And that's why you want these privacy preserving training systems. And so I guess the question I'm interested in is that a stronger model in the sense that if you were, in a formal sense of strong, namely that if you were to protect against that model, do you also protect against this kind of attack?
No.
Okay.
So these are two different types of attacks, basically. One is the attacker who observes, the other one is the one that infers later on with whatever is computed.
I'll catch you later.
Yeah. So you have n numbers, you want to compute the average. Somebody computes the average for you without seeing the numbers, right? Somebody observes the average value, right? These are two attackers. You want to hide the averaging, but also you want to hide the fact that my data was used as one of these end data records.
Thanks.
All right. Thank you, Reza. Yeah, we have the presenter for the next talk come up, please. Sandeep.
Can you flip over?
Hello, can you hear me? Hello, guys. So this is a talk about how we can improve privacy preservation by using a method of personal tagging it at the source. So let me start with some basics. What is log data? So obviously, so we all understand log data is nothing but a record of information, activity of a user, system, or an application. So a lot of devices or application services do log the information about the activity of the user. So log data is always useful to many actors in the systems, whether it's a developer who can use it for debugging, troubleshooting purposes. Also, it could be operationally useful to monitor system performance, measurements, latencies, and of course nowadays for marketing to do analysis on the system to understand what is the user behavior, what is the user usage of a system, of a service, resource usage, metrics, and things like that. And a very important, obviously, the use of log is security monitoring. So we already have a lot of tools which can consume a lot of logs and be able to determine what happened to an event, if there's a security breach, if there is a anti-abuse or a fraud. So logs are very useful source of information to go backtrack and figure out what happened to the system and what went wrong in the system. So this is a basic life cycle of a log. If you look at right from this generation of the log to its preservation, it starts right from the source where a user activity gets triggered, and it could be any intermediary in the path looking at the user flow, either it's forwarding it or processing it. So every system in the path does contribute some information about what is happening to the user and what the system itself is doing with the user and user activity. Typically, we have many devices in the system, so that kind of generate these logs. And at the end of the cycle comes the log preservation. So now the question is, what do you do with some of the log data that you have collected? So there could be, many organizations do invest on tools that have some kind of a protection to the logs that are generated, because we see a lot of logs now being shared with third-party services for either monitoring or marketing purposes, as we saw. So there is always an activity to reform the log, redact it in terms of the data that the log already has, and then eventually give it to a third party or outsource it to different vendors to process the logs and then come out with some interesting information. So if you look at the logs have been there for many decades, right? So we have seen right from the network devices to applications generating the logs. So what has fundamentally changed from the log semantics? So obviously there is more personalization of the log itself. So there is more applications that are trying to pin the user information into a log. So obviously, and another trend that we are seeing is logs are no longer just owned by an organization or owned by a department in the organization. So it's more shared either within the organization or across boundaries or across geographies as well. So largely for kind of purposes that we already saw. And also the log itself is no longer analyzed in silos. So it's basically combined with other events of the user or the system. So there's tools that can do indexing and then come out with a common understanding of what the user or a system or a service is trying to do. So it's no longer just in silos. There is also cases where the log itself can be vulnerable, especially when you're sharing with third-party services. The log data can be vulnerable, which can result in sensitive data leakage. So obviously, OSWAP also has a lot of regulations in terms of how you handle your log data and how do you share it with different parties. And also a very important shift in terms of the log usage is the monetization of the log. So just going from monitoring and management to monetization. So what about privacy and logs? So it's there are already organizations that define log data as part of their privacy policies. They basically address which log data is being collected, how they are using the log data, and with whom they are sharing. A lot of vendors do provide that user policy, log usage policy. But again, the shift is now towards more regulation of the laws, especially from a privacy. The privacy working groups are more focusing on regulating the log itself, the log data itself. So when we look at log, so we see a lot of challenges in terms of how do you identify something that is sensitive in a log? How do you protect the log? So obviously, there are a lot of ways in which we can process the logs, but at the same time, it's very subjective in terms of what a log, what is sensitive data for in a log. So it's something that the application knows very well. So this whether just an IP address is something sensitive or personal, again, it depends on how the log is used and how it's collaborated with other events in the system. But at the same time, we are seeing a lot of vendors providing various tools like machine learning, dataset, dictionary-based methods to actually go into the log, read the log, and find out what is very critical about the log and try to provide a way to mask it or hide it. So I think if you look at what is happening in terms of the privacy preservation or data preservation in logs, so it requires some kind of a framework that we see here, like right from this generation to the point of preservation or privacy preservation. So it starts with log generation. So this is kind of a framework that we can envision in terms of the whole privacy. When you apply privacy to the log, it starts from the generation where potentially you can tag the log with some kind of a metadata. So some kind of an assertion token or whatever, right? Then there are various ways to do that. So imagine if we can, at the source, point to a system that this data that I'm going to put it in a log is going to be very sensitive, or it has some degree of sensitivity to it, right? And that in turn can go into a detection system, so where we don't have to do any specific hard coding. Of course, you can complement this with other existing methods and then be able to detect what is private data or personal data in the system and the log, and then be able to additionally define what you want to do with the data, whether you want to remove the field from the log or you just want to anonymize, mask it, or do anything, any action specific to the log. So, and also you can have different actions defined to different fields in the logs potentially. So that's where we saw it could be differential reduction actions that you can enforce in the log. So based on that idea, so the proposal here is to look at a way in which the source can define some kind of metadata. So as I said, like which can potentially indicate the interesting fields or sensitivity fields within the log that is being generated. So most of us have standard log formats that most applications use. So imagine if you can add another framework or another data to it, saying that while you're defining this log, also look at what is going to be sensitive in the log. So if the source can assert that within at the time of generation, so it could be more useful or more deterministic in the way the data it could be preserved or privacy enforced. So this is an approach that we investigated where you can add something like a PII data within a log. So it could be at the field level, saying that every field you can tag it with a private true or false kind of indicator, or it could be at the log level where you can enumerate all the variables or all the identifiers in the log, saying that this are the private fields. So this is not something new that is happening. There's a lot of precedence in terms of how, or the whole method of identifying data. So here are some vendors that are already doing one way or the other. So each one has, of course, its own way in syntax or a CLI that they define to pretty much define what private data is in what constitutes a private data in a log. So this is, of course, a proposal that has been submitted. So we'll be welcome to get feedback on what you think in terms of this problem statement. So here is some hackathon results. So we just try to put it together and try to compare it with one of the regex-based approaches. So obviously the results is that with an explicit marking, you have, of course, has more deterministic results. With heuristics or maybe a data set based approach, you can get into wrong classifications or something else which is not private data getting mangled. So that's it. It's a very short talk, and so we'll be very interested to hear your feedback and what you think could be the next steps and what can we do from a working group point of view. Thank you.
Hi, Daniel Kahn-Gilmore again. Thanks for this. Your point about the way that logs are shifting globally is, I think, very well taken, and something I don't know how traditionally the IETF has not bothered too much with what happens outside of the network protocol, and this is now starting to look at what gets into what's stored as a result. I think that's useful, but I can imagine there might be some people who are scared about seeing mission creep or something around it. But I do think that we should be addressing it. I'm wondering whether you've looked also at systems for like deterministic or format preserving encryption for logs.
Yeah.
It seems like it sort of fits into this general framework. I know that there was some discussion within dprive about IP address. Was it within dprive? Yeah. I'm not sure, but there was other discussion here at the IETF about that kind of work, and it might be worth trying to fold in these questions about, key rotation and things like that, like what you can do with these when you have fields that you want to scrub. My one other piece of feedback for this is that this seems to take for granted the idea that the way that you identify PII is you say this field is PII and this field is not. And while I think that's tempting from an engineering standpoint, I think it is very unrealistic in terms of what actually personally identifiable data is. Data is identifiable in combination and not as specific fields. And so you could, my name is not personally identifiable because there's somebody else who has my same name.
Yeah, link.
But that in combination with say the state that I live in is. And so maybe the name is not PII and the state's not PII, but the two together are PII. And so this is a problem with the concept of PII itself. But I think we need to be careful about enshrining that in our data representations.
Yeah, that's a good feedback. Thank you.
Yeah, I guess I'll just respond as to your last point, DKG also. I think we were it's definitely like a 0-0 draft thing that we're just saying that PII equals true. I think definitely agree that that's not that's not sufficient. I think one thing we were looking at was sensitivity level. So you could maybe classify certain fields as belonging to a certain set of fields, like in terms of how sensitive they could be in combination with others. And then you could have a policy where if there's too many of these, then you say that, oh, redact all of them. That's something we did think about.
This is Vittorio Bertola from Open Exchange. This is interesting. We have actually been trying to address this at a basic level because it's actually a problem you have whenever you have an application that generates logs. Today, in Europe at least, you have to defend and protect the personal information, even just the IP addresses that are in the logs. So we have been experimenting with, for example, encrypting the IP addresses in place and in a way that they can be later decrypted if necessary, but with proper procedures in case of monitoring, law enforcement, and this kind of stuff. So maybe it would make sense to have some kind of best practices across the industry on how to do this in a consistent way, even if each application, even for the same kind of service, has different log formats maybe. But maybe some discussion on general principles could be useful so that we get to a good way of doing this.
Okay.
Wes Hardiker, ISI. Two comments. One, actually, to DKG's point. The IETF has a lot of protocols that actually ship logs around in various formats, including everything from actually shipped straight in DNS. They're shipped in syslog. They're shipped in syslog-ng. They're shipped in netconf. They're shipped in there's actually a lot of places where log information is sent SNMP. So I like your approach a lot. There's only one question that I had with it, which is you specifically said no hard-coded rules, and I don't understand the motivation for that, of why you wouldn't do both hard-coded rules and machine learning, because hard-coded rules are pretty much a guaranteed ground truth, always will match, because I'm removing a username field that I know about, whereas if you just let the machine learning component take over, it just may get a 80% chance of removing that sometimes.
Yeah, can you just repeat it, because I think the question was about no hard coding. Was that?
So go back a couple of slides. That one. Nope.
This one?
Yeah, so you said detect personal data and you had no hard coding.
Okay.
And so I would think that you would want a combination of an automatic, machine learning based approach and, expert knowledge where it's always right.
Yeah, that's a good point. So obviously it's going to be like a complement to what methods are already there. So just that it could be another input for a machine learning model to see, okay, this is the indication from the source that the degree of sensitivity could be there. So that way it could be used.
Well, specifically, I would think I would use the log detection mechanism, and with that augment it with expert knowledge at the end, so that the redaction took both the fixed hard set of rules and the machine learning component, and then did either or of them. You would remove that.
Either or, yeah.
Just channeling Chris Lemons from Comcast from Jabu. I think this was in response to DKG's comment, which is what happens off the network is often a consequence of what happens on the network. It's easily in the scope, in my opinion.
What happens off the network?
What happens off the network is often a consequence of what happens on the network, and it's easily in the scope in Chris's opinion.
It's a good point.
Ben Schwartz. If you're looking for a place at the IETF to do this kind of work, I would suggest narrowing scope here, or narrowing generality, and trying to look very specifically at a specific existing systems that generate logs. One that comes to mind is HTTP request logging, which is, of course, almost universal. That's a case where the IETF has substantial authority, and if we, for example, identified different kinds of different specific header fields that should be logged differently in different circumstances, that's something that we could reasonably make a recommendation about. I also know that there are people out there who believe that servers will log their HTTP requests in different ways, and have encoded assumptions about that into how their clients behave. So, for example, I've seen assumptions in systems related to DOE that requests of the form GET will have their full query path logged, but requests that are formed as a post will not have the post body logged. Right. And that is in fact a popular, that is consistent with implementation, but it's not something that's ever been documented and standardized. Maybe it should be.
Yeah, I think that's agreed that generalization is a tough part here, because some of the vendors that we are seeing, they're again focused on a very specific type of log that they want to provide the redaction. So they're very specific. For instance, they only look at a HTTP packet, or they only look at maybe a CFL kind of a formatted log. So, but I think you're pretty right in terms of saying that we have to narrow the scope of what we want to do.
Yeah, one reason to keep it general was to it was a very deliberate decision to keep it like a research document, trying to explore the space essentially. But I agree, like if subsequent drafts try to make it more narrow, that would belong in the IETF.
Thank you.
Allison Mencken, Salesforce. Thank you for the great presentation. I support adopting this as an IETF document. Just to come back to something that that Ben just said, I think you don't really have the option of being very prescriptive, but you can actually provide. I mean, you can, but it won't be standard. But you can provide questions and guidance that can later be valuable into the standards process. A thing that struck me about that was, I mean, there's a saying that the best logs for privacy are the ones you don't retain, and you gave this great statement that people have more and more reasons why they're retaining and using logs. Perhaps this document could also talk about kind of a time limit, like at a certain point, you really have made a tremendous loss of privacy by keeping it beyond that point, and give some of the reasoning for that. And that might help to advise people to improve their policies. I don't know if you have a comment on that.
Okay. So I think it also depends on the privacy policy itself, right? I think there are a lot of organizations, the regulations that define what is the timeline. I think it's a good input, but we'll have to look at it from the privacy policy point of view and see if we can put those guidelines. But you're right in terms of identifying a specific time limit, as you said, right? It should be useful at some point of time. We have to be more pragmatic about that. Agreed. Thank you.
It's Chris Lemons of Comcast in the Java chat again. Consider the audience who will read this document. People who write drafts that standardize or generate logs might be a good set of members for that audience.
Sorry, I didn't quite get it. Can you repeat it again?
Yes, I'll repeat that. Consider the audience who will read this document. People who write drafts that standardize or generate logs might be a good set of members for that audience.
Okay. Thank you.
All right. So there seems to be some interest in this document, and there's some overlap with work that's going on in the IETF. Can I get a quick show of hands from people in the room who have read this? So a couple hands go up. How about a show of hands of people who are interested in this particular topic? A lot more hands noted. Okay. So I guess based on that, I'm going to do a hum for adoption right now. So the question is pretty simple. If you support adoption of this particular document into the research group, please hum now. And if you do not support adoption, please hum now. All right. So there seems to be stronger support for adoption. Of course, we'll confirm on the list and go from there. And if you have any comments on the document in the meantime, please, reach out to the authors or send them on the list as well. That'd be helpful. Yeah. Thank you.
Thank you. Thank you.
All right. Hello, everyone. My name is Chris Wood. This should hopefully be very quick because we talked about this last meeting in Montreal. where there was a talk similar to the ANRW paper that was presented, and we presented some results that were similar to it. So this is just going to go over the document that we have sort of describing the network-based website fingerprinting problem and ask you some questions. So some background for people who were not there in Montreal and don't really know what I'm talking about. Website fingerprinting very vaguely or broadly is this class of attacks that basically try to use metadata of some sort to figure out some sensitive application data. So a common example of this is looking at metadata from TLS connections, like the sizes of records or the timing of records that are sent over a particular connection, and trying to infer what application data is sent. Equally, it could be looking at the IP addresses of a particular connection and trying to infer what the service or domain a particular connection corresponds to. We're not being super specific with this particular definition because it's just generally about using metadata to identify a particular website or service. And so this document sort of was born out of discussions with Ian Goldberg and Tao Wang, who are heavily involved in the Tor community, basically asking whether or not all the attacks that have been done on Tor are sort of relevant to or applicable to things that we would do on the IETF. And moreover, to what extent are these attacks applicable in practice, and do they scale well to the internet? So in trying to get our heads around this, we basically went and looked at a bunch of research papers that were published on this topic and summarized them both for our own knowledge and hopefully for the benefit of others who potentially read this. Here's the outline of the document if you have not looked at it. So basically it goes and describes the general problem, describes the known attacks that are in these papers, describes some defenses that are also been experimented with and have been deployed in practice to some extent, particularly in the Tor space, and then ask some open questions for how these might be relevant for existing IETF protocols or IETF protocols going forward. So pretty straightforward, very similar to Joe's draft on censorship tech, in the sense that we're just surveying existing stuff. So my question to the people here are, first, is this useful to anyone besides me? Because in writing this down, I had to read a lot of papers, and that was useful, so I learned something from it. Maybe it's useful to the IETF or IRTF, who knows? And if it is useful, should this happen here in PEARG or elsewhere? Who knows? Does the scope need to change? Should we take things out, remove things, whatever? And similar to Joe's draft, this is sort of problematic because the nature of this document is whenever a new paper is published, I go in and summarize it and put it in, and that sort of implies that publishing something that's sort of stable is not perhaps the best way forward. So I will defer to the mic.
I mean, that was a lot of questions.
I know.
I mean, yeah, go. I mean, yes, this is absolutely useful. There's like a long list of mechanisms that allow, that allow passive or active observers to determine what your, web browsing behavior is. And, once we finish removing all the ones that just state flat out what your web browsing behavior is, eventually this will become the easiest way to do it. And so getting a handle on how to fix that seems super critical. I think PRG seems like the place for this. It's hard to see where else it's going to sit. I don't think HTTP really is going to know what to do with this. I think the output of this work, what recommendations for what HTTP should do to actually make fingerprinting harder would be something you could feed into HTTP. I agree. Probably having an RFC doesn't seem super helpful because it's kind of static. I don't know, maybe the IRTF publication process is lightweight enough that you could crank out a new RFC every year or something. But the existence of this document seems super helpful. I would encourage you to keep at it. And I guess I don't know the IRTF process well enough, but adopting as a working group item to signal this is something that we think is important certainly seems valuable.
Yeah, and maybe with respect to the how frequently they update the document. Maybe the approach is just make it a GitHub page or something, and then I just update it there and point people to it from the PEARG thing. I don't know. Like,
Yeah, I see Colin's like way behind us in line, so maybe he has an opinion on how this ought to work. But in any case, I think this is good work, and you should keep at it.
Thanks.
Yeah, I totally agree. I think it's useful for IETF, and I think IETF. I think folks, you're going to get wider readership from folks who just like with the censorship draft, people walk up to me and they're like, "Wow, this is really helpful for a number of reasons," and they've never, touched protocols. I think the scope is right. I do wonder if there's going to be a way to capture things that maybe don't make it necessarily into the academic literature. I know that's where you sort of started from, and maybe that's something to think about. Like what level does it reach to make it in there? And I guess in terms of being living, I don't know, other than there's nothing wrong with having an ID that gets updated occasionally and peeled off if we need something to point to as canonical. But yeah, I don't know if I have anything useful to say there. But
Yeah, thanks.
this is Joe from ISOC.
Just to clarify, the criteria for the criteria for putting something in this document was very low. It had to do something with website fingerprinting, and it had to show up in my Google Scholar alert. So that's pretty much it.
This is Daniel Kahn-Gilmore. So thanks for this. Seconding the previous commenters, we definitely need this work. The framing of website fingerprinting, I think, is maybe a little bit confusing given the way that we're talking about HTTP as transport these days. And so it might be worth trying to think about what we want to talk about there, right?
Yeah, I'm a bit unhappy with the term website fingerprinting. That's just what's used traditionally in the literature, typically because like it started off in Tor in that particular way and they've just carried it forward. So yeah, if there's a better term to more accurately capture what we're trying to actually do today, I will happily use it. Not sure what it would be.
Well, so what's interesting is that it used to be that you'd say website fingerprinting because you were distinguishing between that and other forms of network traffic fingerprinting. But now that most network traffic wants to be HTTP traffic in the first place, all of a sudden we're back to kind of network traffic fingerprinting.
That's a good point. Yeah.
So I'm not sure what that balance is. As far as the live document or whatever, please keep working on it. Let's have revisions for it. If it turns out that it's useful to say, here's what we think network traffic fingerprinting looks like in 2020, that's a perfectly legitimate document to produce as long as we continue to revise the baseline draft that produces that, so that maybe we want another one for 2025.
Yeah.
But yeah, I do think we need a place to collect this information, and we need a place to point people to when they start designing new protocols, as they inevitably will, that make these same mistakes again.
Thank you.
Just like giving up on the mic stand here. Yeah, okay, I guess it's okay, fine. Got to go back to first principles here. This is Richard Barnes. I'm just going to plus one all the comments about this being valuable work, and DKG mostly cover what I was thinking about, extending to non-web applications, because like everybody uses HTTP now, and concerns for fingerprinting what apps are on your phone are very similar to fingerprinting what websites you're visiting. As far as stability, like I wouldn't be, it doesn't seem like we would fail here if we produced a snapshot at the time and revisited at the time. I think one thing that could be done to give this a bit more longevity is to think about whether there's some abstractions one could make over the techniques in the literature, and to discuss general classes of attacks, and kind of call those out as guidance for things people to consider in designing protocols. We did something similar a few years ago. A few IAB folks and I did a draft about censorship techniques, ways you could do blocking, where we talked about generic classes of approach to that problem, so to speak, and ways that in the advantages, the ways they could be deployed and the things they break. And so I think a similar approach could work here. I haven't, I admit, dived into the document in real detail, but that would give this document a bit more longevity.
Yeah, good suggestion. We haven't taken the time to sort of try to generalize anything. It's really been just a brain dump of what we've discovered in the literature, but that's a very good suggestion. Yeah, thank you.
Hi, Colin Perkins. We'll see if this microphone falls down before I finish talking. I think this work is useful. I think this research group is as good a place as any to do the work. I don't have any objections to that. In terms of the living document type thing, if you've only ever published RFCs via the IETF side, I think you'll find the process is perhaps lighter weight in the IETF. Yeah, I mean, XML v3, but you know, it means you can add pretty pictures. No, but I mean, seriously, I think you're keeping this sort of thing alive as an internet draft and occasionally pushing out snapshots as an RFC makes a lot of sense. You know, this is the state of the world as of 2020 or whatever it is, and then just keep it ticking over, and then in a couple of years' time, well, we'll publish another one. Okay.
Yeah, that seems reasonable to me.
Yeah, we got plenty of RFC numbers, right?
Cool. Yeah, I might as well. Yeah.
Is anyone opposed to us asking for adoption right now? Please step up to the mic right now. Okay. So all those in favor of adoption of this document by PEARG, please hum now. All those not in favor of adoption, please hum now. Perfect. Same, we'll take it to the list also, and yeah, take it from there. Thanks, Chris.
Yeah, thank you.
Bernie, are you in here? Oh, perfect.
Good afternoon. My name is Björn Hüneisen. I am having a short presentation to frame the discussion of the next document as presented by Iraklis. So there's an activity going on called Meetup, Missing Elements for Decentralized Usable Privacy. And it has the following background. So we are working on solutions that are decentralized, end-to-end, peer-to-peer. For reasons of mitigating the adverse effects of pervasive monitoring, because it's an attack to privacy and has been documented even in RFC. And centralized elements are usually more prone to attacks, because if you have the centralized element, you have everything. And if it's decentralized, the effect is limited. Usable, because message encryption is a hassle for most internet users. I mean, who of you has already tried to set up PGP? Not so many. Who of you managed to do that in less than 1 hour the first time? Okay, a bit less anyway, but who of you would consider that people who are not attending the IETF, who are doing something completely different, are able to set up a PGP client? Okay, 0. And that's actually where it comes from. We need to fix this usability challenge by automation, because people are simply not able to do it on their own if they're not getting enough help. And that's where it's coming from, this usable. And privacy, we consider privacy as a human right. So this MEDACT activity, in short, I can't go into all the details, but basically it's about enhancements to application protocols for decentralized usable privacy. And it's based on opportunistic security. The whole thing emerged from the initiative of PEP, Pretty Easy Privacy. It's a foundation that is doing implementations in this area. But it's not limited to that. It's also like other people working in the field, for example, Autocrypt, are invited to participate and actually actively contribute to MEDAP. And the goal is to define the missing pieces like key management, private key synchronizations, message formats, trust words, handshake, etc. I can't go into the details of this. We meet in so-called non-working group sessions during IETF meetings, with the exception of this one. We are not having this kind of sessions, otherwise we had it the last 3 IETF meetings, I think. We have a mailing list set up, meetup@ietf.org, and you can subscribe there if you're interested in the field. And at some point in time, we are aiming for above to be an IETF working group and work on this a bit more in a broader sense. So what's there so far? All these boxes represent an internet draft. I don't know how much time we have that I can go into details of all the boxes, or should I just summarize?
It'll give more time to Heracles.
Okay, yeah, right, okay. So basically then I talk about the 4 corners, like the pink corner is more or less what has to do with handshake and trust. Then there is the application corner, which is the brown corner. For example, use it in email, but also instant messaging. And we are even using it for banking transaction. For example, the SWIFT network is using the same technology. Then we have the private key synchronization area, like that you have different devices and generate the key with one. The others use it to encrypt your email and read the email on the other devices. Usually don't work unless you share the keys. And we have a solution for that. It's already implemented. And the green area is like the core area with requirements, the core stuff. And what you hear as next is a basis for that green area. It's the threat analysis that out of the threat analysis that is discussed in next presentation, the requirements are coming, or part of the requirements are coming. So now we know where this next presentation is fits to, and I would hand over to Heracles then.
Heracles.
Okay. I might need the speaker, maybe not like, okay, let's like that. So, hello everyone. Thank you for PEARG and IETF for inviting me and for this long-standing contribution. I want to break this presentation. Actually, it's a call for to stimulate discussions and to call for contributions. Under the keywords, I'll break down the title of this presentation on these 4 points: a systematic analysis of security and privacy threats for private messaging. And when I'm talking about private messaging, I'm talking about emailing and instant messaging. Okay, I'm Heracles Meonidis. I'm a postdoc at the University of Luxembourg, and this is a joint work with PEP, with Bernie Hoensen and Nana Kerlter. Sorry. So, very quickly, it's still a relevant problem, private messaging, in mail and instant messaging. So just quickly in the numbers, I'm not going to spend too much, 3.7 billion users email, with the future predictions even more. We see a little bit dropping on the private use, but still like 75 billion users approximately of emails. Here, just to say on these numbers and the statistics that these two messaging applications actually belong to a single application provider. And we see this distribution roughly, I would say 80% of the world is under a single service provider. So do have a systematic way of analyzing the threats and the requirements. What is usually being done in the RFC at the FERT SMTP 821 back in 1982, we built it, IETF built a very nice system, SMTP, but initially without security into consideration. So we found out a bunch of threats, for instance, to list one, man-in-the-middle attacks. Then we started designing systems that had like client-server encryption, like StarTLS. And we had all this nice analytics of Gmail showing it to our browser, like, oh, your flight is at that time, you should consider going because there is a traffic or not. And surprisingly, in 2013, we got this Sprint project with Snowden revelation that it showed us, oh, by the way, this information is not going only to you, but is going to some Secret Service analytics systems. So we shouldn't consider trusted the servers of email servers and these messaging servers that they only keep the information only to ourselves. So we start building end-to-end encryption as MIME. We thought that centralized systems, they might even not be that robust and privacy preserving, because they might send different public keys. We have OpenPGP, and this summer we had this spoofing of certificate poisoning, which I'm not gonna go into technical details, but essentially they break up OpenPGP because they made it very buggy and large, start signing certificates, and they made very large and buggy certificate, and then when you download it, it actually was breaking OpenPGP. Okay, we found out ways to have end-to-end encryption with great security protocols, but then now what? There is a header problem with metadata, and this great person, the general for NSA director, said that, well, by the way, we might not know to what you are saying, but we kill people based on metadata. And even there are like academic work, very good academic work, or like projects successful, but still there is no application. So where are we now? There is a lot of academic work, but usually the approach is like, we think that these threats are very relevant. But if we do it the other way around, we start mapping the list of threats, and we start like, instead of running after the attacks, we start designing systems by very beginning. So EFF started to, on this direction, try to evaluate and try to make a list of design security features, but this specific as a website, but this is limited categories, is obsolete right now, and it evaluates only existing apps. So the aim of this internet document is about to assess, to have a security and privacy threat model and requirements, and a holistic systematic approach, and for assessing existing systems, or when designing a new systems, you can use it as a guideline. And this takes into consideration technical threats, security and privacy, but also the user threats. There is keep on discussion on intelligence service about backdoors, and this is not a technical vulnerability. This is an issue of opening a backdoor in your system, and this is a user threat. So we think that as a basis for private messaging, maybe it's a good fit for later on for IETF, and maybe PEARG to consider adopting this as a working item. Okay, what is in the internet draft? What we have? What is our contribution until now? So as I will show you a little bit later on, we have a system model. We define the system model, meaning what exactly? The entities and the functionalities, which are the adversaries, what the adversaries can do, the class of threats, the class of requirements, and later on, in a later phase, in this document or in a later on, we will have the risk approach, because now we consider the threats uniformly, but maybe you want to evaluate the threats. And then, which are the crypto protocols we have, or the crypto primitives, for instance, OTR. So, if I am to say the system model in a whole, it could be that Alice and Bob want to communicate and want to exchange messages, or it wants to exchange emails or instant messaging using instant messaging systems. And here we have the networking nodes, And we have split it, the trust establishment, which is essentially to have identity, key, and contact management, and third parties. And what we can do is we can start playing with the threats, with adversarial models. And when we say adversarial model, we are talking about whether an adversary is a passive. We say honest but curious. It tries to not break the system, but it tries to extract as much information as possible. It can be active adversary, and can be internal or external. And here's the list that we have started compiling. And this first list, the first 2 columns, is about security threats and security requirements. And this is extracted. This is a methodology that's being used by Microsoft with a Stride framework. So essentially, we try to find out all the possible threats in these classes of attacks, classes of threats, and the corresponding requirements. So the same thing as a methodology we did it with privacy. Privacy we used an academic work called Linton, which we adapted it for our needs. And I want to highlight 3 specific points. So for confidentiality information disclosure, this is a threat to security and privacy. However, for non-repudiation, it might be a requirement as a security, but an issue to privacy for privacy. It can be an issue. And it's actually how OTR has been built that has plausible deniability. So having a map of threats and requirements, we can at the very early stage, point what we need to do. Another thing is the privacy interdependence. Think about the case where you're installing a WhatsApp or a Signal, and all your contacts go to the cloud. And there is a matching who has this application. So essentially what do? You send your whole social network to the cloud provider of WhatsApp to do the matching and notify you who has the same contact, who has installed the same application. So in Signal, there was a lot of discussion how you can do it in a privacy-preserving way. So we might have recall the previous slide. It's not only metadata about who we're communicating, but also like with whom we have exchanged information. We have our contacts shared. So just a case study just to show you what we can do with that, what we can do with this internet document, and what we have done is we start discussing about, okay, if we start placing an adversarial model that could be, for instance, the email servers, we can have protocols as StarTLS, which can preserve confidentiality, entity, and data authentication, but we consider, what about if we start consider email servers as passive adversaries? Honest but curious that will constantly try to read our information, to read our email and instant messages. Then we start playing with, for instance, a SMIME. We thought that, okay, what about, I don't know if it is, okay, here's correct. So what about if public keys that are being shared are spoofed, for instance? I'm using a public key that's supposed to be for my friend Bob, but it actually is not. We have this issue of certificate flooding, as I said, which in specific a third party, we can frame it as third party, an external adversary is aiming to break, to do a denial of service attack. And in this particular case, Bob is considered as adversary, and OTR has been designed considering these very principles of confidentiality, entity, and data authentication, forward secrecy, and deniability. So we can start picking threats that we need to design a system for, and we have specific countermeasures, and having the whole map of adversarial models, we can say exactly what we need to do. Instead of going the other way around, saying, I believe, which can be, as an expert, we can have a very good overview of what is needed, but we think that as a systematically, it's even more important to do it as we can see the whole map of threats. Future directions. Well, there's a lot of work that needs to be done. So usability issues on OpenPGP and PGP has been discussed in the previously, and there are 3 academic papers from 99, 16, and 06. So we have a key management issues, and still the problem remains about how we can use it, how we can make it more usable. So that can be another issue and the requirement that we need to design our system, that we need to consider our system design so that not only design it in an engineering way, but also like to make it practical. So there is a lot of push from intelligence services with different arguments about backdooring, and this is like very recent news about US and UK and Australia to just start backdooring. And we think Australia already passed a law, but I think that it's not active, they say. They haven't activated. And as there is a human right and a law of the privacy of correspondence of emails, you cannot open the mail in a non-war times. The same should apply as a reasoning, the same should apply in the digital world. And finally, there is a lot of discussion about post-quantum crypto, and there is a call by professors and academics and experts in the field that we need to start considering moving towards that, because the time that will pass, so companies to adapt to design new protocols, it takes time. Information that we are storing in our system needs to keep it for 10 to 50 years. So we already need to start designing new systems that would consider post-quantum security. Instead of running afterwards, we need to be proactive. So that's all from my side. If you have any questions, it's very welcome. Thank you.
Ben Schwartz, thank you for giving this deep thought to the important topic. I definitely support this work in this area, and this draft seems very well written. But I had a few comments about this. I think that this is a fairly opinionated draft. It doesn't seem like a neutral summary of the field. It seems more like a coherent framework that you're presenting. I would suggest giving it a name, essentially presenting it as a new named framework. I would also suggest thinking about it as a framework instead of describing it as an analysis, or especially using the word requirements, which occurs a few times in the draft. Certainly at the IETF, requirements refers pretty specifically to setting yourself up to do specific protocol-based work, and it doesn't seem like that's the real purpose here. I would clarify the scope some. Some of the research I've seen here suggests that, at least for ordinary users, if you ask them what kinds of security threats they're worried about in private messaging context, the things that you listed here are not at the top of their list. The things you listed, the things that they tend to list are insider threats, things like people peering over their shoulders or their boss checking their phone while they have it in a locker. Those are really important security threats, and it's fine to make them out of scope, but we should clarify scope. And I would suggest thinking about this in terms of communication, not just messaging, both because I think the technology itself doesn't matter, and because what we're really thinking about here is communication between people, whatever form that takes. In particular, video chat and related stuff, I think it has important privacy concerns that we should be thinking about.
Thank you very much. I would suggest to take it offline and go point by point later on. You tell me exactly, and Thank you very much.
Mr. Bertola, Open Exchange. I just want to be sure that I understand what's the objective of the work you're proposing, because, I mean, are you trying to write a set of requirements to then design yet another instant messaging protocol that this time will be private and secure? And so, because I think that, as was already pointed out, first of all, in the scenario in email and in instant messaging is pretty different, because in instant messaging you only have walled gardens, and when you have walled gardens, there's no way you can exclude whoever runs the server or the service you are using. So that's already, I mean, a basic problem for any kind of privacy and security you want to grant. With email, it's different because you could choose your server, but still you have lots of other things to address. But also, I mean, having spent some time trying to I mean, in the real world, convince some big email operators to just adopt existing technologies like DANE and DNSSEC, for example, to make the email transmission more secure. I agree that the problem, this problem is not very high in the requests of the users or of the people that runs the servers. So if you really want to advance the discussion, maybe there's non-technical things that we should discuss. If you want to put this only at the technical level, then I would like to understand what's the objective, so what you want to achieve in practice.
So the objective of this internet document is to do it in a way of mapping the threads in the technical aspect from the very beginning. Instead of pointing later on, we have this thread, let's try to patch it, let's try to figure how we're going to design a system. So this is like for evaluating existing systems and protocols, or if you want to design a new, and if you are a security engineer or a privacy engineer, that you will be able to see which are the threats, what you need to do, what are the existing systems, crypto primitives, protocols. One point that you said, I don't know if I've covered with my answer. We can also take it offline. One thing that you said is instant messaging and emailing is different. Yes, but one is low latency, the other is high latency. Well, nowadays, both systems and in the messaging aspect, they both have common points with both. If we just remove the XMPP, if we just remove the SMTP, like the transport, how we transport and the format, if we see it like as what we need to safeguard, so we send text, we set attachments, and we have archiving or searching. We have.
I agree that technically, I mean, we are working on chat over IMAP. So I mean, that's not. What I was pointing out is that they are very different in the architecture of the market and the service that people actually use. So it's a non-technical difference.
Okay. Thank you very much.
I mean, this is an interesting space. I guess I'm a little less sanguine about this particular document than Ben is. As Vittorio was saying, like trying to like span email and instant messaging and video strikes me as extremely difficult. Like the MLS work here has like a fairly well-defined threat model in the architecture document that tries to like map out what the threat model is. But a lot of it's actually fairly specific to like the MLS setting. And if we tried to like expand that to email, I think it wouldn't work very well. And I think actually part of like as an example of that, the slides you have about like how awful PGP's interface is, like basically don't apply to any of these messaging systems, which actually have extremely streamlined, key discovery and setup. They have like all those other problems, but they don't have these problems about like key discovery that are complicated. So I think trying to like have some document that like is a master document like for all model for all messaging, like just ends up with you like rating like a cryptography textbook, and like and describing Dole of Yao, which is like not super helpful. So I think I guess I would encourage you, given that like that we have existing work in the IETF that is like designing security for instant messaging right now, to like if you want to work on the instant messaging problem, to engage there, and if you want to write like an email for analysis, like this might be an okay place for this, but then this document needs some revision to like actually be that.
So I don't know if I understood correctly the question.
It wasn't a question.
I don't want to say OpenPGP or PGP is awful. Okay? No, I don't. That's not my point. what I said is we have some facts and some analysis of whether it's working until to which extent or which issues we have to be considered, like based on the academic work that exists.
Just time check, 1 minute.
Yeah.
Just be mindful.
So this is more like here in this room and in IETF has been done. There's a lot of expertise and there has been done a lot of work. So it's more like a call for discussion. Instead of doing things like I do believe, or like maybe we set up, like we start doing as a systematic way of threats and identify the whole spectrum, like bringing the expertise everyone has, and then have an internet document that will help and guide others that would like to design, engineers that would like to design.
Right.
Is it like, did I answer your question?
Well, again, it wasn't a question. I guess what I'm saying is that like this document would not be helpful for designing MLS. It would not advance the state of the art. It might be useful, some other version of this document might be useful for analyzing email, but if you want to contribute to the design of the protocols we're actually doing here, then I don't think a document that's abstract is going to be very helpful.
Very quickly, Richard.
Richard Barnes. Yeah, I'm on a similar page to Ecker. I think, I agree that this is an important problem, that the state of messaging security, especially for email, is really terrible. But I don't think it's because we don't understand the problem sufficiently. In contrast to Dr. Wood's document about fingerprinting, where there is like open uncertainty and active research about what the threats are, I think we actually understand the problem pretty well. And even in the MLS case, where we're writing a document to document the threats we're addressing and the architecture for addressing those threats, that's more about kind of consolidating on a view and making sure that everyone's on the same page, because everyone already had fairly detailed internal models, all of the vendors who were coming to the table for MLS. And so that was more of a consolidation effort than research, really. So I think this is probably not appropriate work for a research group here.
This is DKG. So I think I agree with Ecker and Richard that this document might be too broad to be particularly useful. In contrast to what Ben was saying, Ben was suggesting, well, maybe we could abstract it even further. I mean, the way you had split up your architecture looks a lot like you could use it to discuss IPsec, in that you have trust, association context, and then you have the actual messaging security, and you have the transport, all of these things, right? You could actually evaluate IPsec with the same framework that you have, but at some point it becomes vague enough that it's hard to know what's actionable where. With regards to whether this is actually useful for research, Richard, I think that the work on eFail in the last year shows that we actually still don't understand the scope of attacks against email, against end-to-end protected email. And I actually do think that it would be useful to try to document this for a specific application domain like email, because I believe that there actually is more. I mean, we've done such a bad job of defending against the attacks that we do know about for email that no one feels like it's worth showing that it's even more broken than it is. But that doesn't mean that it isn't actually also more broken. And so I do think that there's actually room, given the evidence for like the low-hanging fruit that we saw from eFail, there's room to identify more problems there. And so I don't think this is going to be fallow ground for research. But I do think that it needs to be more scoped to be useful, more tightly scoped to be useful.
Hi, Mallory Nodal from Article 19. It was a question. I didn't understand what you were trying to document. Was it that how the actual threat is compromised, or is it the threats themselves? Because I think what you're trying to do is look at threats from bring user level threats into the conversation, which would be very useful. But now after these comments, I'm not so sure that's what you're doing.
Okay. User threats, it's mainly this document's about technical threats. Which threats can be the classes of threats, and what actually does it mean in a private communication, private messaging system. In a future consideration, we need to think about we think that we should also consider as user threats in terms of, but this can be in another document, not in this one. It's just this one, I try to capture all the directions that we think of that should be, but it's not in this document.
So for
I'm sorry. We're way over time. Can you take this offline, please?
Sure. Yeah.
All right.
Mhm.
Great.
Thank you.
Thank you, everyone.
That's right. Yeah. Did you want to?